Okay, class. What we're going to talk about is the extreme case of the Doppler effect. Meaning like Doppler gone wild. Whoa! Oh no, gone wild. What does this mean? He's so crazy? No, not so crazy. What we mean is what happens when the source of source, moves the speed of sound or even faster. Now, how fast is this? Well, 6 suddenly 767 miles per hour or 343 meters per second we are talking about. So it's very fast, yes? Okay. Now, what takes place is quite dramatic. Remember, we're talking about the Doppler effect for sound in this case. Let's take a peek. What we have is a bunching up, as you can see at the top here, of the wavefronts. Now we can see that the source of sound is moving to the right. But instead of the waves just kind of collecting next to each other, they're literally bunching up on top of each other. Now I have very good, simulation that I'd like to show you in class. So make sure you remind me about the simulation to show you in class. Now, as they pile up on top of each other, something very interesting starts to happen. Do you remember about sound waves? Sound waves consist of high pressure and low pressure spots. So every single front that you see represents, for instance, a high pressure spot. And in between are the low pressure spots. If they're all piled up on top of each other, that means that they are high pressure and low pressure almost experienced simultaneously. If you exceed the speed of sound, right now this is going the speed of sound, what would it look like? How about this? Down here we can see that now we have a cone shape that's been formed, and if we take this line and this line here, we can see that it's very conical in shape, and this is what we consider above Mach 1. This is what we consider, if this reaches your ear, a sonic boom. Very loud, very startling. The louder it would be dependent upon the energy it contained. So we can make a sonic boom that's not quite as loud as you may experience, for instance, at an air show. And we will make a sonic boom in class tomorrow. Yes, in class tomorrow. Once again, this shape here is called a Mach cone. Let's take a look at some pictures, yes. Here is a bullet. Special photography is employed. This bullet is traveling at what we call Mach 0.99, just under the speed of sound. The speed of sound is considered Mach 1, and you can see there's a nice bow wave forming in front. This bow wave here is a high pressure wave. Here is a bullet traveling faster than Mach 1, Mach 2.45. This particular bullet has exceeded the speed of sound more than twice the speed of sound, nearly 2.5 times the speed of sound. And that bow wave has now formed a conical or a cone shape, what we consider a Mach cone. In this particular case, all the regions of high and low pressure will be piling up on top of each other, delivering a large amount of energy to whatever region it passed by. Here is what we call a rocket car. This rocket car is traveling in the desert very fast. How can you tell it's so fast? Well, obviously it looked like a rocket, but it has wheels. Rocket car, yes? And you can see slight distortions here. See these distortions? There are slight distortions in the visible light that's traveling past the region where the rocket car is also passing by. Why, I ask you? What could be causing such a thing? If you recall, the compressions and rarefactions, or the high pressure and low pressure, build up. And so we are seeing a building up of high and low pressure regions. That is causing a density difference in the air. And as the light travels through the different density of air, it causes a sort of effect or a bending that we will learn about in the next topic called, do you know what it's called? Refraction. Yes, refraction. So this car is the first vehicle, land vehicle, to travel faster than the speed of sound. I have very good video I'd like to show you in class. Yes, remind me, please do. Now look at this one bogus. This one better. Yeah, this is a hornet-breaking sound barrier, and I want to point out the strangeness of this cloud that forms around the plane. Now, if there are enough moisture in air, cloud will form around the plane when it goes faster than the speed of sound. Why? Why, I ask you? Remind me to make cloud for you in classroom. Yes, I make cloud for you. It'd be fun. We enjoy. Remind me to make this cloud. But essentially, cloud form when moisture in air that has been already evaporated is in gaseous form is cooled to the dew point temperature. What is dew point temperature? Simply temperature at which the evaporated air or the evaporated moisture in the air condenses, forming dew. Commonly what we call it. Not same dew as in our class, but different kind of dew. So as this plane breaks sound barrier, rapid compression, then expansion with low pressure following behind the compression. The expansion causes the air to expand rapidly, cooling the air. Remember back to some thermophysics we talked about last year, and we talk more later this year. But as the air expands, cools the air down to the dew point temperature. If there be something for the moisture to condense upon, it will form a cloud like this. Very unusual, very neat to see, yeah? Now I have 3 video, and then I'll show you the video now. I show you in class. So remind me in class to show you 3 video. Sometimes you see the sound barrier being broken. Sometimes you hear the sound barrier being broken. I ask you how you see, what it look like. I ask you what it sound like. You will find out. Now, I wait at this point to show you a demonstration of a sonic boom in the classroom. So, when we pick this up tomorrow in class, I give you sonic boom in classroom. Oh, it's very startling, but not too bad. It's very loud, but not too bad. It's very fun, but not too fun. Talk to you later. Bye-bye.